The purpose of today's video is to investigate the trends that exist in the ionic radius. Now these trends are a little bit different because there is not a single trend as you go across or down the periodic table. Instead, we need to consider the electron configuration and the common charge when we make our determinations for ionic radius. So the first thing we're going to review are the common charges that exist for the elements in the main group of the periodic table. So that's our S and P block. Remember, elements in group 1 tend to form +1 cations. Group 2 tends to form +2 cations. And then if we jump to 13, that's our +3 cations. 14 are +4. 15 tend to be -3, then -2, then -1, and finally remember the noble gases generally don't actually form charges. Now, we do need to look at these anions though, because in fact, it's not the entire groups that really wind up forming the anions. Instead, I'm going to draw a box here around these 11 elements: nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine, arsenic, selenium, bromine, tellurium, and iodine are the elements that generally form the majority of the ions that are the common ions we'll be looking at. You can also absolutely include astatine, although really astatine is pretty rare anyway, it's incredibly radioactive. The other elements that underneath these, they actually wind up usually forming the cations with those charges that we discussed in the last chapter. Even though they're in the group of the anion, they're just so big that it's incredibly difficult for them to pull any more electrons in. So usually you will see these down here as being cations. Now that we've had a little bit of clarification on that, let's look at an actual example. The first thing we're going to discuss are the cations. And remember, cations are just positively charged ions. So these are generally metals. I'm just going to write that down here so we don't forget. These are usually our metallic atoms. They're usually metals. And our cations, when we're looking at their radius, we're going to need to consider how they became positively charged. So if we think about the magnesium atom, we have our Bohr model shown with the electrons in the appropriate energy levels. If we want to compare magnesium atom to the magnesium ion with its common charge, we need to think about the fact that magnesium is in group 2. Remember, elements in group 2 have those 2 valence electrons, and it's a lot easier for them to lose those 2 valence electrons than it is for them to gain 6 more electrons to become stable. So usually the magnesium ion is going to have a +2 charge. And in order to obtain that +2 charge, it lost not just the valence electrons, but the entire valence shell. That entire energy level is now gone. So if we compare the atomic radius to the ionic radius for magnesium, it's pretty obvious that the ions are a lot smaller than their neutral parent atoms. And again, that's really just because they've lost their entire energy level. So, quick review, cations are positive ions. They are usually metallic, and when they obtain their common charge, they lose an entire energy level, which then causes the size to get much smaller. If we compare that to an anion, something like nitrogen. Nitrogen atom looks like this. So we've got the 2 electrons and then the 5 electrons for a total of 7. Nitrogen ion is going to form by gaining electrons. Specifically, it's going to gain 1, 2, 3 electrons to get a full valence shell. Now, when we're looking at that, it doesn't really look like much changed. It didn't gain another energy level. It didn't lose another energy level. These nonmetals, these anions, just put electrons into the energy level that already existed. But by adding those extra electrons in, what we have increased are the repulsions, the repulsive force between those electrons. We didn't add more protons in order to balance and pull in anymore. So instead, all we did was add more electrons, which will actually cause that shell to get a little bit bigger as the electrons just push away from each other. So now, even though it still only has 2 rings, the actual size of the anion got bigger. Remember, anions are negative ions. They become negative by adding electrons in to fill up the outer shell. These are usually nonmetals. And the ion is generally larger than the neutral parent atom because you have more electron-electron repulsions. So once we understand the general trend for cations and anions, the other thing that I'm going to ask you to do is compare the ionic radius of something that we call an isoelectronic set of atoms. Isoelectronic just means that they have the same number of electrons in the same energy levels. So right now, the atoms that I have drawn would not be isoelectronic because they each have a different number of electrons. But if instead of comparing the neutral atoms of each of these, if I instead compare the ion that each would commonly form, now you might see exactly how they have the same electron configuration. So, if instead of sodium neutral, we compare sodium plus 1. Sodium plus 1 becomes a +1 charge by losing that 1 valence electron. Magnesium becomes a +2 by losing its 2 valence electrons. Aluminum becomes a +3 by losing all 3 of its valence electrons. Silicon becomes a +4 by losing all 4 of its valence electrons. Phosphorus is actually going to become a -3. It's going to gain 3 more electrons. Sulfur is going to become a -2 by gaining 2 more, and chlorine is going to become a -1 by gaining 1 more electron. So these are the actual ionic radii that we now want to compare. Now it should be pretty obvious that we can kind of divide these into 2 general groups based on how many energy levels they have. Even though all of these elements started off here in period 3, these lost an energy level. So now they only have 2 energy levels, whereas these gained electrons within the energy level, so they still have 3, which means we could probably fairly easily divide them off based on how many energy levels they have. And then we could say that this side, the negative side, is definitely larger than this side overall, based on the fact that they just have a whole extra energy level. These 3 atoms would be isoelectronic because each of them has a total of 18 electrons in their 3 energy levels. These 4 atoms would also be isoelectronic because they have a total of 10 electrons in their 2 energy levels. So we have 2 groups that are isoelectronic that now we need to compare to each other. So it would be completely understandable if you were to assume that because they have the same number of electrons in the exact same locations or energy levels, that really they should be the same for within each group. However, there is something that's different, and that's the number of protons that are pooling on those electrons. So if we look at the periodic table, sodium has 11 protons, magnesium has 12 protons, and aluminum has 13 protons. Silicon has 14 protons. Phosphorus has 15, sulfur has 16, and finally chlorine has 17. And we can use the number of protons that are pulling in to then rank these isoelectronic sets. Remember, the more protons you have pulling in on the same number of electrons, the tighter the atom's going to get. So of these three, the smallest of the three is going to be the one that has the most protons pulling in. So we could say, now let's erase this so we don't get confused later, we could say that chlorine minus 1 is the smaller of our three anions. And then sulfur minus 2 would be next in line because it has 16 protons, which is slightly less than 17, so it doesn't pull in quite as much, but it's going to pull in more than phosphorus, which only has 15. So for our anions, the larger one was P minus 3, then S minus 2, then Cl minus 1. If you're comparing anions that are isoelectronic, the larger negative charge is a bigger ionic radius. Larger negative charge, so the minus 3, is bigger than the minus 2 or the minus 1 because it has less protons pulling in on those electrons. For our cations, our positive ions, again, the more protons you have, the tighter the pool is going to be. So now the thing with the most protons here is our silicon. Silicon is going to be the smaller, and then we would just keep going backwards in that period. So silicon's the smallest, and then aluminum, and then magnesium, and finally sodium would be the largest of the cations within that period. So for cations, a larger positive charge is actually a smaller ionic radius. So let's add that understanding to our boards from before. We know that cations are usually the metals. We know that they're smaller than our neutral parent atoms. And we know the bigger the positive charge, the smaller the cation. If we're thinking in terms of our anions, we know that they're usually nonmetals. We know that they're larger than the neutral parent atom. And we know the bigger the negative charge, so the negative 3s, the larger the ionic radius becomes. So we could absolutely now rank in terms of isoelectronic series. So these that had 18 electrons versus these that had 10 electrons. Or instead of looking at an isoelectronic series, we could also still just look across a period. So this time let's jump down and let's consider period, let's go with period 2. We'll go back up a period, just so that we can avoid the d electrons here. Think in terms of the elements with their charges. So lithium has a common charge of +1, beryllium has a common charge of +2, boron has a common charge of +3, carbon is +4, nitrogen is -3, oxygen -2, and fluorine is -1. I'm not going to include the actual noble gas since it's not charged, and right now I just want to look at the ionic radius. First thing we can do is separate our cations from our anions. we know the cations are going to have less energy levels, so all of these are going to be smaller than all of these. These are going to have an extra energy level still. And then we think about our general rules. If we're looking for the smallest ionic radius, we're looking for the things that it's the most positive. So that's going to be our carbon +4 is smaller than our boron +3, which is smaller than our beryllium with a +2, which is smaller than our lithium with a +1 charge. And all of these are going to be smaller than our anions. So then we've got fluorine with a -1, smaller than oxygen with a -2, and then finally nitrogen with a -3. So kind of think of it like a number line, +4, +3, +2, +1. If we considered noble gases, if we were just looking at radius and not ionic radius, the 0 would go in here, and then -1, -2, -3, which we can then take that understanding and identify some things on the periodic table. So the next couple of things that I talk about here are not super duper important. They're general ideas about the periodic table, but it's not like it's going to be a 10-point question on a test at any point. What I want to do is I want to look at the entire periodic table, and I will look at the common elements, and I want to try to figure out where are the largest and the smallest cations and anions. So let's start with an easy one. Francium is the smallest positive charge you can get, +1, which means it's kind of in the middle. And it's as far down the periodic table as you can get, which means it has the most energy levels. So francium is going to be our largest cation. On the other end, the +4s near the top, carbon should be our smallest cation, but there is a little bit of a caveat there. I'm actually going to label that as the second smallest cation, because even though it's a +4, which puts us at the smallest end, there is actually one cation that's even smaller, and that would be hydrogen. Even though it's only a +1, it literally has no electron cloud left. All it is a proton, so that's the smallest cation. But if we're looking at the general trend, carbon, which is near the top and over to +4, that should be where the small guys are. So largest cation, smallest cation. And then for anions, the smallest anion is going to be the least negative, so that's our -1 group, and it would be up near the top. So this would be fluorine with a -1 is the smallest anion. And as far as the largest anion goes, I could absolutely see where you would say astatine, if we actually wind up with an astatine atom, that would be kind of small, or even, kind of big, or even tellurium since it's a little more common. But to be completely honest with you, a lot of places are even going to label arsenic as the largest anion, and that's just based on this rule, where in order to get the largest, we want something that's as negative as possible. So this would be the -3 group, and it's as far down before we start getting those positive cations back again. So again, these 5 are going to be labeled on some of your periodic tables for you, but it's not absolutely imperative that you memorize all of those. I would say the largest cation and the smallest anion are things that definitely follow the trend, so you should probably know those. And then just remember, as you get further away from him, you're going to get smaller in terms of cations, and as you get further away from him, you're going to get larger in terms of anions, and you should be able to answer any question that I pose. If there is anything about ionic radius that you don't understand, please feel free to reach out. Otherwise, we only have 2 more trends for the chapter, and those will go very quickly.